Well, so the purpose today is to answer questions, talk about methods or things that might be on the exam, look at study problems. So initially, are there any particular questions on homework problems or any review problems? So for the exam, you can have a couple pieces of paper, write some notes on both sides. Bring a calculator, check that the batteries are working, be okay. On that you can write formulas, you can write numerical examples, you can write sentences for describing what a confidence interval is, or what a hypothesis test is, and so on. But we can also look at one of the final that was from last year. We can start looking through some of those questions. There's a couple other sets of problems there. So if we do these, you still have things to study. So in this one, a researcher is looking at water temperature in degrees Celsius and amount of dissolved oxygen, milligrams per liter on 70 days on a creek in California. And there's a picture of the scatter plot there. So what would you say would be a description of that scatter plot? Not too strong, not at all. Slight decrease, probably, right? There's some lower points over here, and not so many low points over there. So a slight decrease, but pretty weak. So if it asks for a description, describe a couple of features, maybe a trend, how strong it is. Are there any outliers? Some smaller points down in there. Range 10 to 20 degrees Celsius. Right? And so that's a pretty wide range, and so on. So describe the relationship. The second question, here's the linear regression output. The largest point on there, the largest temperature at 20.5 degrees Celsius, and dissolved oxygen at 6.6. What's the error in the prediction line? So this one we have to get the prediction line and then calculate the difference. So we have a point. So the output of R or minitab or everything generally kind of looks like this, right? There's an intercept or constant line. Sometimes this one's called constant. And there's temperature or maybe X variable, grade projects, and homework. And the estimate, and so our prediction is going to be 11.19 minus 0.16 times X, where X is the temperature. And so this particular point had 20.5 is the X value for temperature, and 6.6 is the Y value for that. And so to do the prediction, we need to put in the X value, 20.5. I thought I printed the copies of all that, so maybe I didn't. Here we go. Right, so the prediction calculates to 7.91 milligrams per liter. The units in terms of the oxygen. And so our error E is the Y value minus the predicted. So the Y value tells you there is 6.6, and the predicted is 7.91, so taking those differences is negative 1.31, and that's also milligrams of oxygen per liter. But these are the intercept and slope came from here, and then putting together the regression line, and then plugging in a value for that. So each increase in temperature of 1 degree Celsius is only making a 0.16 adjustment in the dissolved oxygen, so it's not so much. Thank you. The other things that are in there, standard errors, t-values are used in testing. And so the next question is this a significant relationship? Is the slope significantly different from zero? And so we'll go on to talk about the next page. So the first one, we're looking at this regression problem. And so out of that information, the slope is negative 0.16, and the standard error, okay, the standard error for this is 0.06. And if we wanted to test the hypothesis that the slope is 0, no slope, no association, versus the alternative that the slope is not equal to 0, we're going to calculate the t-statistic, that's the estimate divided by the standard error. So with negative 0.16 over 0.6, and it turns out to be negative 2.67. So is that a large t-statistic for this problem? Is it far from 0? So in regression, we'd have to compare it to a certain t-distribution. We use n minus 2 as the degrees of freedom, and our book says 97.5 tail. So the book, it says there were 75 streams. So n in this case is 75 streams in the data set. 75 days. And so with 73 degrees of freedom, there's 0.975. If we look at Rosner's table, his t-table, this one, if I can get it to go. Okay, that's get rid of that stuff. 75, we don't quite have on here. But and this column is the one we're looking for. That's the 0.9751. Right, so it's going to be somewhere in this area. Right, 73 is going to be between these two. So 1.99 would be reasonable to use. You could use 2 or 1.99. So we're going to use this at 1.99. That's our cutoff value. If it's bigger than that or less than the negative of that, it's extreme. So what do we conclude? No, we're going to reject the null hypothesis. And there he is, a negative slope. It's rejecting the null hypothesis. It's not 0, and we saw that the estimate was negative, so I can conclude there is a negative slope. So the relationship is significant. It didn't look like it was very strong, but there's enough data points following this general, this slight decreasing pattern to be statistically significant. Another thing you can do is this is a confidence interval for the slope. Confidence interval for the slope, so 95%. Confidence interval for the slope data would take the b plus or minus this t-value of 1.99 times the standard error for b. And so it's negative 0.16 plus or minus 1.99, the standard error was 0.06. And 1.99 is about 2, and 2 times this is 0.12. So this interval, if you subtract 0.12, it's negative 0.28, and then up to negative 0.04. There would be a 95% confidence interval for the slope, right? So how much does an increase of 1 degree Celsius, how much does that impact the dissolved oxygen? Well, it looks like it's going down somewhere between 0.28 and 0.04 milligrams per deciliter. Per 1 degree Celsius, actually, for rate of change. So, but anyway, that's the where we think the slope is. We estimate it as negative 0.16, and probably in that range. Is it consistent with the hypothesis test? It's all below 0. It doesn't include 0, right? So, and that's consistent with rejecting 0. So that's a regression table. The regression type problems probably are accompanied by a plot. You know, maybe the table, a table like this, scatter plot. It's talking about prediction, residuals, and things like that. But any questions about the regression? There's a couple of regression problems in the other sets of things that would ask similar type of things for practice. Second problem, we had a table here, men without with prostate cancer. The study were randomized to surgery or just observation without surgery. And the outcome is do they die or stay alive? What are the survival rates of the two groups? It's just a two-way table calculating rates based on the counts. So what's the survival rate in surgery? When surgery is this column, survival rate means alive, 264 out of 327. The fatality rate would be the 83 out of that would be the death rate. So that's 0.761, and then observation, observe, had 242 out of 348, 0.695. So it's lower by about 7%, almost 6, a little over 6%. Are these significantly different or not? You could either do a hypothesis test or a confidence interval. You can write them both down on your formula sheet if you want, but you could look at the confidence interval for the difference of two proportions, and then see if it includes 0. If it doesn't include 0, then they're significantly different. If the confidence interval goes positive to negative, then 0 is in there, and maybe they're the same. Or you could do a hypothesis test. The solutions are posted on this. So why don't we could look at one, and then I'll let you, which one do you want to look at? Do you want to do a confidence interval or a hypothesis test? Yeah.
Hypothesis test?
Yeah, we can do a hypothesis test. If you want to see how the confidence interval will go, you can look at the solution. Okay, so hypothesis test says that the two rates, I'll just call them P1 and P2, are the same. The alternative is that they're not equal. And overall, and for a hypothesis test, we need to be composite. If the two groups were joined together and there's really no difference, what's the rate? Right, the survival rate then is 506 over 695 from the table. So overall is 0.728, which is between the two that we have there. For hypothesis testing, we're going to calculate a z-statistic. We're going to do p hat 1 minus p hat 2, and then p hat 1 minus p hat, and then there's a sample size from the first group and a sample size from the second group. The square root of that is our standard error. So we're going to calculate that z-statistic, compare it to a standard normal. If it's much more than 1.96 or less than negative 1.96, then these groups are going to look different to us. So this 0.761 for the surgery group, 0.695 for the observation group. The composite between those two things is 0.728, and 1 minus that is 0.272. And we had pretty decent sample sizes, 347 and 348. We'll copy the number from the table and the square root of all that. Do all that calculation, the z value is 1.95. Pretty close to 1.96. Round it, it would, would like. What did we conclude? Can we reject the null hypothesis? Just barely misses. If the 0.975 percentile for a z is 1.96, our statistic, our z value, is just less. We do not reject the null hypothesis at the alpha equals 0.05 significance level. It doesn't quite make it. Right? Does this mean that that surgery isn't advantageous? Does this mean that maybe there is a real difference, we didn't have enough sample size, power?
There be some difference, but statistically speaking, no.
So in this case, we, statistically, it's within the range of error, just barely. Maybe if we redid the study with 4 times as many subjects, if these differences persisted, maybe it would, come to show it. Maybe we've made an error. Maybe there really is a difference and we were just unlucky. And the survival rate in the surgery group was lower than it typically is, or the survival rate in the prostate, in the observation-only group was higher, and so the difference looked smaller than it really is. So maybe we made a mistake. And there's a chance of that, right? That would be a type 2 error. Not that you need to get that technical with it, but it's possible that there really is a difference and we failed to reject it. Or, that we just didn't have enough sample size to get a pretty good chance of it. Bigger sample size is more likely. So anyway, we don't quite reject it. Yeah.
So, but you would reject it if it's less than 0.05?
Less than the 0.05 significance level.
Right.
So if this had been 1.65, it would be a little bit bigger. We do not reject H0 here, right? Because z equals 1.955 is less than the cutoff value, 1.96. We want our statistics to be big and away from 0, and that shows a big difference. We're not quite far enough out. We're very close. I'm sure they were disappointed. Hypothesis, the one special thing for a hypothesis test in this case, right, is we had to do a p-hat because the null hypothesis says they're the same, and we do that. The solution's also described, so that's described there. This is the confidence interval formula. The confidence interval doesn't have that assumption that is not equal. If you do the confidence interval, it actually ends up being just above 0. Just if you do the confidence interval, you would conclude that just barely it is statistically significant. I mean, this is how close it is. It's like a p-value over here of like 0.0501. We'd still be best to publish it and report the results in either case. It's really close. And here's a chi-square test, right? This is a 2x2 table of counts. The rows, the totals on the sides don't add that. But here's a chi-square result.
Can you just go for 1 second, please?
Yeah.
I'm kind of confused. So the confidence interval, you're saying to reject it?
It's just like right at the,
Yeah.
so this standard error this is a funny case where the change of
They're
the
so
standard.
similar.
They're just so similar. It just came very, very close.
Okay.
Right? This is like 0.001, just the calculation, because the standard deviation is just as like this is one of these cases right on the boundary, because the two formulas are slightly different, you get slightly inconsistent results. But both of them basically say you're at 5%. It's at the boundary,
So-
no matter what you say.
If that was like on the exam, do you want us doing both confidence interval and hypothesis?
No, just one is fine.
Okay, so that
Whichever
would
you
go
pick.
both- that would kind of have to go both ways though, right? Because,
So if you do, yeah, if you got this hypothesis test and did it, yeah, so there's, I think the answer is, it's at the border
Yeah.
in either case. If you did a chi-square, it's like equivalent to the hypothesis testing. So the chi-square hypothesis test, there's this p-value in there, the chi-square statistic value is 3.79. The p-value is 0.05, so it's not quite significant there. That's consistent with the hypothesis test. How would you do that chi-square? How would you do some chi-square calculations related to that? So we had this table here of died, survived, and this one is surgery and observation. And there's 83, 264, 166, and 242. We use a chi-square in a table like this to say, are the two variables independent of one another? Or are the rates of survival the same in both groups? So if we have a null hypothesis, right, it can be stated as rate of survival is equal to the two groups. The alternative is different rates. Well, under that null hypothesis, if they're equal, right, then the survival rate should be determined overall. 506 and 695. So that the overall survival rate, 506 over 695, was 0.728. If that's the same rate, we can calculate expected values in a table like this. So out of in the group during surgery, there was 347. Out of those 347 values, if 72.8% survive, we would expect 0.728 here. And 347, the other percentage, 272 would go up here. If it's the same survival rate in the observation group, there was 348, we would expect 348, 0.728, and 348, 272. And those would be our expected values. So I might ask you about chi-square by showing you the output, like in this one. I might ask you to say, well, what would you expect for one of these categories, like survival in the surgery group, if it has the same rate in both groups? I don't have those particular numbers. Calculator, we could just do that quickly. So we expect 347 times 0.272, or 347 times 0.728. And the other one is practically the same, right? 348 times 0.27. It was a randomized study, so they're basically the same numbers. So in terms of expected value, this table recounts 347, you'd expect 94.4 over here, you'd expect 252.6, and over here you expect 253.3, no, expect 253.3, wrote it in the wrong place. And then this one you expect 94.7 with a little bit of rounding, right? And what we actually got in our data, we got 83, but expected 94. We got 264, but expected 252. So they're a little inconsistent with that. And that's it. But not enough just for us to end up saying that it's probably statistically significantly different. It's really close. Yeah.
Is there any like reason why like the top two and the bottom two are so similar? Does that mean anything for the study?
Yeah. So in the randomized study, they both had about the same sample size, right?
So it just happens to be that they were just.
Yeah. So if these are about the same sample size, under the assumption, like these expected values, we use the same percentage. We use the overall percentage of these two things. So they started out with about the same denominator, same sample size, same rate under the null hypothesis, and so these two expected values are virtually identical. The data that was used in this, there was a third, oh wait, that's not it. Okay, that's that one. This third question, scientists measure two types of woodland salamanders and measured them in many ways. One set of measures was tail length in millimeters. There's 20 red-backed salamanders with an average standard deviation of 17. Calculate, so this says the calculated pool standard deviation and so on. And the solutions show how to do the two sample problem. I don't plan to ask you a two sample problem for means. We did that on exam 2. The plan is to do a one sample confidence interval for this type of setting. And so let's see what that looks like. So I would take off on number 3. Right? We had, for the red salamanders, it was 20. The standard deviation for those was, well, X bar was 3.2, and the standard deviation was 0.9 millimeters. With a confidence interval for the average length in this group, X bar plus or minus a t-value times S over the square root of n. That t-value is the 97th percentile with n minus 1 degrees of freedom. So we want that 975 column with 19, grab the t-table. And these smaller numbers are on the t-table. We have the t, yeah, these smaller numbers. So we want this 975 column, the 19 value is 2.093. Row 19 for degrees of freedom and 2.093 for the next one. A little bit bigger than 1.96. We need a little bit of spread because we're estimating the standard deviation. So this formula in this case is 3.2 plus or minus or 2.093 and then 0.9 over the square root of 20 as an interval. Okay. So that would be a 95% confidence interval for where we think the average tail length of this species is. The last year's exam asked about the two sample comparison. This one, we're going to plan to ask this type of question and talk about the confidence interval. So you calculate that, the R, so we have a number there. Oops. Right. 3.2 plus, and then I can do kind of a minus and a plus. 2.093 times 0.9 over square root of 20, and I get 2.78 up to 3.62. That little C thing with the -1 means to subtract it on one side and add it on the other. Multiply by -1 if you want to do it both times. Little shortcut. And so the interval is 2.78 up to 3.62 millimeters as an average. All right, so you can do that with the other one, similar thing. Degrees of freedom change. It only had 17, so you're gonna have to look up 16. The question goes on, and so we're not going to do that per se. A third group was also observed of green-backed salamanders. And here's box plots of the three groups. Do you think that the groups will be significantly different or not? It would be an average difference.
Yeah, red and green won't, but
There's red, lead colored.
from the other two.
Yeah, so red and green might be quite similar. Maybe they're not significantly different. Right? But the red ones look different from this, the lead colored and this one. Those look significantly different. These, maybe. It depends on sample size. Right? So I took some summary statistics from another book and had simulated some data and used it on this exam. The data I still have, right? And the green ones, the mean red length is that, the mean of the lead ones is that, and the mean of the green ones is that. I'm not sure if that corresponds to the data there exactly, but I put them together in that dot, the box plot. Let's see what these things look like. What are the names of the variables? The names of the variables. Tail, I just call it the tail length. Right? So the box plot of the tail as a function of color for these data. Right? Oops. It just means it wants to see it. Right? Like that. Similar pattern to the things on there. To test that type of thing, right, you could do analysis of variance, LM of the tail as a function of color and data. If you do that, we get this output in there. That's an ANOVA table then for testing, is there an effect for groups? Based on this table, what do we conclude? Is there a significant effect by species in terms of tailing? And you go to the conclusion over here, you get F value of 11. This scientific notation means very small, right? 4 decimal places and then a 6. So the 6 is the 5th decimal place. So that's much less than so the corresponding here for analysis of variance, the null hypothesis is the average tail lengths are equal in the 3 groups, and then the alternative is the average tail lengths are unequal in some way. One group could be different, or they could all 3 be different. And the p-value over here as the very simple summary, less than 0. It's actually less than 0.001. It's very small. And because of that p-value, we reject the null hypothesis. It is not significant. So that's kind of the quick summary. There's some difference, and it looks like from the graphs that there might be multiple groups that are different. With this analysis of variance table, there were, let me just peek there were 55 salamanders total. Salamanders. Between the three groups. So when you're looking at the ANOVA table, there'll be the color or species that's in there. There's an error or a residual, right? And total. There's a degrees of freedom that goes there. Right? And then the sum of squares and a mean square and F and a p-value. Given this information, how do you calculate degrees of freedom? What do we put in that column? What would be the degrees of freedom for groups?
3 minus 1.
3 minus 1, yeah, this is 3 minus 1 is the 2. Right. Error. Yeah.
I think that'd be capital N minus 1.
This one, n minus 1 comes down into this one. Right? So we would end up with 54 down here. And this one is actually n minus I, or the number of groups. So n minus 3 in this case. So this is the 52, and then they add up. Now, if I told you that the sum of squares is 13.4, right? I said this is 13.4 over here. What's the mean square over there? Mean squares are sum of squares over the degrees of freedom. So we'll take the 13.4 over 2, and that's 6.7. This other sum of squares was 29. 29, some 29.7. So this one's 29.7 over the 52 for that one, and that's, oh, it's 0.57, 0.58, right? 0.58, and there's a 9 in here. So it's 0.58, less than 1. And so the F is the ratio of these two things. And that value is this big, 11.6. And the p-value, which I would give you, is some indication if it's small. Anyway, you won't calculate the full table, but I could ask you to take, explain the degrees of freedom, or explain the relationship between something kind of going across. Any questions about that? The last problem that was on this one had Los Angeles Mayor Tom Bradley was predicted to win in 1982 based on X, but he lost by many votes. Shows that 45% of voters support Bradley, and that voters who support Bradley will stop to answer a poll 40% of the time, but voters who support the opponent will stop to answer 30% of the time. What percent of voters stop to answer an exit poll? Right? So this is going back to the conditional probability, maybe making a tree, right? In this case. So on this one, there's a tree where there's Tom Bradley as one candidate, and George Deukmejian, right? And 45% for Bradley, so that means 55% over here. And then if they're going to answer the poll or not, is the other one. Right? And so if nobody's stopped, none of supporters of Tom Bradley would stop, then nobody would say it. The perceived percent would be 0. That would be extreme, right? But 45% also, 40% will stop to answer the exit poll. That means 60% won't. And for the other candidate, 30% and 70%. So the chance that you're in this row, these are the two places where you actually answer, you take the 0.45 times 0.4 there, and then 0.55 times 0.3 there, so that's 0.18, and that's 0.5, that's 0.65 there. If you add those two things together, you get 0.345. So a little less than 35% of people actually answer. The 35%, 0.345 is between the two fractions of 30 and 40. Right? A little bit weighted more towards, it's a little bit below 0.35 because there's more people at that lower rate. So what percent of the voters who stop to answer will support Bradley? What's the chance they say Tom Bradley, given that they actually answered? Right? What is the news going to be picking up on in terms of predicting the chance of him winning? As I move this, it will. This is relative number 5. So we want the probability that they say Tom Bradley, given that they actually answer. And the Bayes theorem, kind of the inverse of this, well, you get both things here over the probability that you answer. And this is the probability that Tom, that the preference, and then they answer, right, to reverse it. So answering was 0.345, 45% supported here, and 40% stopped. So this is 0.18 over 0.345. And I don't know what that is exactly, it would be in the solution. But importantly, of those people who answer, more than 50% are saying Tom Bradley, even though only 45% are voting for him. So the response at the exit poll, because of that differential, make it inaccurate. So if you got to the point of having the table, you could just take 0.18 over the 0.345. Tom Bradley, among those answered, is 0.18. Answering overall is these two parts of it. So the answer to this one is 0.180 over 0.345. Once you have the chart, if it's easy just to go directly to that, because that makes sense, that's fine. What I wrote before is kind of showing a few more of the symbols and kind of making, but it's getting the same answer. So. Well, that was kind of what was on there. One thing that's not necessarily on there is a normal calculation. So what was this? There was some description that I gave of different types of topics. So focus on those. Right? Focus on those and review these type of problems. Those sections from the exams 1 and 2 on those things. Not everything, but the ones that we talked about. You can have a piece of paper so you can write notes and things. Any questions on homework or other topics? All right, well, you've been a fun class. I hope you've enjoyed it.
Could you go back to that last page though?
Yeah, this one?
Yeah.
This one here?
Yeah. I didn't copy.
Oh. Give me that one. So right, if you have the project or homework, you can drop it off. We'll try to have things graded and then email you if we can hand things back on Friday for the exam, but I'll post it in place.
I printed my job and having like.
Okay. I'm gonna take a look at it. Every once in a while.
Okay. I wasn't sure like.
I don't know. I Sounds good, I'll take a look at it.
Yeah, I mean, Oregon and Washington.
Okay, sure.
I've never,
What?
Thank you.
Sure, thank you very much. Thanks.
Have No one's what? No one's qualified because literally everyone is
For what?
She sent you a presentation. We accidentally did a presentation.
Well, you made a presentation.
Yeah.
Instead. Oh, okay. I
And we
haven't
also
seen
did
it yet.
the essay.
Okay.
So you could just like, disregard that.
Okay, well,
Yes.
I mean, that would, that'd be a bonus.
Oh, really?
I mean,
Do we have to present?
you don't have to present, no, yeah, no, just the size of it, it would take us
Yeah.
3 or 4 days to
Oh.
have it present. So there's no presentation, it's just a write-up,
Yeah.
but it's, if anything, it will, be a favorable thing towards that. If you
Yeah.
made up a presentation, a paper, and then thought about how you would present it, that's good.
It was just an accident. It just happened.
Yeah, so,
Thanks.
Sure.
I was waiting for the hand. Oh, also, do you mind if I run to my next class? My last class, grab my homework and put it in your mailbox?
sure, that's fine, yeah,
Okay.
yeah.
Grab that. If you're not here, I'll just. slide it
Yeah,
in.
or you can slide on the door, I'll be there for a couple hours, I think, still.
Thank
so,
you.
yeah.
oh yeah, could you do the same for my homework, because I forgot to print it out.
Yeah, so if you can print it and get it to me
Yeah.
today, that would be great, so. The TA will pick it up later this afternoon, so if you can get it in the next couple hours.
Yeah.
An hour or two, then that would be awesome, because then you can do it efficiently, get it all done.
Yep, see the finals.
See the finals, yeah.
Thank you.
Thank you, Leah.
Do you happen to know what these are?
No, I mean, that different, they've been up for a couple of weeks, that whether it's education, I mean, I know there's some education classes that need them here for something. So it looks, yeah, middle school to high school, or the
Mental
age
health.
is just, yeah, things, changes, going on. Like they say, eighth graders, there's a lot of things about emerging identity and changes. So something in a reading and study for that class has been up for a while.
What age does your brain slow development? Or like stop? It's like in your early 20s, right?
I think so, but I think there's some evidence that there's some element that might still keep going, but it's, and then so the importance of continuing to have mental stimulation and avoiding drugs and things that would dampen. So it's a little bit more complex, but I think it slows down a lot, but maybe not completely stopping, so. Some days it feels like mine's declining, but it's, you know.
I feel like anyone that studies math has a lot of stimulus. 'Cause that's one of those classes that you need to
Yeah.
have a lot of logic to make sense of everything.
Yeah, so, you know, I think it should be fun. I think, you know,
Oh.
music or poetry or something where you're looking at complex relationships and things, you know, I think there's a lot of different things like that.
Music
Yeah.
and poetry.
Yeah.
Have a nice day.
Thank you.